In the previous class, we looked at the row echelon form. So in this lecture, what we'll do is that we'll slightly improve on it, and we'll also understand what were the matrices that were being multiplied on the left. All right. So let's look at the definition of the elementary matrix that were being multiplied on the left. So we start with the definition and then we'll generalize the idea. So definition, a matrix E belonging to Mn of C or Mn of R, whatever you want to talk of. So it is set of all n cross n matrices with complex entries, with complex number as entries. All right, entries is called an elementary matrix, is called an elementary matrix if it is obtained by applying exactly one. That's very, very important. Exactly one elementary operation, elementary row operation to in the identity matrix size n. All right. So what are the things? So there are three of them. So let's look at things for n equal to 4. So you have to take n is equal to 4 in all these examples. The first example is multiply the ith row by C belonging to R or complex number C not equal to 0. All right. So there's the ith row here and C is here. So the notation for this is E I of C. This is what the notation is. All right. So this is notation. Fine. So for example, if I want to look at E2 of 5, E2 of 5 will be, since I'm looking at n is equal to 4. So it is a 4 cross 4 matrix. Fine. Second row is being multiplied. Fine. So second row is multiplied. So second row of identity is this. I multiply C to it, and this gives me 0, C, 0, 0. So this is my second row, 0, C, 0, 0. All right. There is no change in the first row, no change in the third row, no change in the fourth row of the identity matrix. All right. So this is the first row of identity matrix, third row of identity matrix, and the fourth row of the identity matrix. So this is your E2 of C. Second is replace the ith row by ith row plus C times jth row. So I'm replacing the ith row. So I'll write EI. Many books they follow the other notation. So IJ, and I'm replacing by multiplying by C. So I write like this, EIJC. This is the notation. So for example, if I want to look at E13 of say 2, then what we are doing is first row has to change. So let's write things here. So first row of identity plus 2 times third row of identity. So first row of identity is 1 0 0 0 and 2 times the third row of identity, so which gives me 1 0 2 0. So this is my first, because I'm replacing the first row. All right. So the first row becomes 1 0 2 0. There is no change in the second row, so it remains as it is for the identity part. There is no change in the third row, and there is no change in the fourth row. All right, so this is my E1 tree. Fine. The third one is interchanging the ith row and jth row. So this we write it as Eij. Fine. So if I want to look at, for example, if I want to understand E24, then E24 will be, so second row of this is same as the fourth row. So if you remember, the fourth row is supposed to be this, fourth row of identity is this, fine. Second row of identity is this. They are supposed to be at the second row and the fourth positions. So my first row is still the same. There is no change in the first row and there is no change in the third row. All right. So these are the elementary matrices of three kinds that I have here. Right. I would like you to understand that there are some important implications as far as matrix multiplication is concerned. So let's multiply them and look at examples to understand it better. Let's example. I'll look at this example only for 3 by 3 matrix so that I can save some time and understanding is anyway there for you. All right, so first is multiplying, say, so I multiply the first row by, there's nothing in the second row, nothing in the third row, fine. I look at this, so this will be my E1 of 5, 3 cross 3, so n is 3 for me. I'm looking at this is E1 of 5. Let's fix A. So I'm fixing A as 1, 2, 5, 0, minus 1, 0, minus 1, 1, 0. So if you want to compute E1 5 of A, I would like you to see that this is same as multiplying the first row by 5. So it is 5, 10, 25. Second row, there is no change. Third row, there is no change. All right. In my notes, I have computed E2 of 5 times A. So what is E25? E25 is there is no change in the first row. Second row is being multiplied by 5. Second row of identity, all right, fine. Third row of identity comes here as it is. Multiply by A. And I would like you to see that there is no change in the first row. So you'll get 1, 2, 5. Second row is being multiplied by 5. So you just multiply 5 here. So 0, minus 5, 0. And then minus 1, 1, 0. This is what you will get E2 of this. Fine. Similarly, let's compute E12 of minus 5. So E12 times A, so let me write times A here. So E12 of minus 5 that I'm looking at is first row. There's no change in the second row. There's no change in the third row. And the first row, well, let's look at here, the first row, this is the identity, first row of identity, minus 5 times the second row of identity. Second row of identity is this. This gives me 1, minus 5, 0. So I just put it here as 1, minus 5, 0. Multiply this to A. And I would like you to see that this is nothing but the second row remains as it is. The second row remains as 0, minus 1, 0. Third row remains as it is. Fine. And the first row, if you look at here, what you're doing is this. So first row remains as it is. So it is 1, 2, 5, minus 5 times the second row, 0, minus 1, 0, which is same as 1, 2 plus 5 is 7, and 5 here. So it is 175 that you have. So just write 175 as it is, fine, 175. So this is the matrix that you have, fine. I don't need this because the calculation has been done. So I can just delete it here, fine. Similarly, if I want to interchange, if I want to look at E12 of A, E12 is, so this is the second row, this is the first row, so I'm interchanging the first and second. Third remains as it is, multiply by A. I would like you to see that this is same as 0, minus 1, 0, 1, 2, 5, and minus 1, 1, 0. All right. So just try that out yourself and you will get all of them. Is that okay? So this is about multiplying matrix on the left. Multiplying elementary matrices on the left. All right. So what you have seen is that when I multiply matrices on the left, so this gives us this. So this operation gives operations on the rows of A. That's important. This means, so I'm looking at elementary matrix E times A, and this is what it does. So E gives an operation on the rows of A. That's okay. All right. Now let's look at from the column point of view, what does I do? So as columns, let's understand. So use this idea to look at row multiplication. That's all I'm saying here. Let's look at column multiplication now. So I want to look at A times E, and want to understand it. So let's do the same thing that I did earlier. So A is fixed for us. So I want to look at A times E2 of 5. So A remains as it is. E2 5, if you remember, it was first row remains same, second row is being multiplied by 5, third row remains the same. So I would like to see here is that the first column of A will remain the same, the first column will remain the same. The second column gets multiplied by 5, so I get 10 here, minus 5 here, 5 here. And third column remains the same, so I get 5, 0, 0. So just verify it for yourself that this is what it is. Fine. So columns are being multiplied. All right. Similarly, A times, the next was E1, 2 of 5, E1, 2 of minus 5. So A remains as it is. E1, 2 is 1, minus 5, 0, 0, 1, 0, 0, 0, 1. So the idea here is that this part still comes from elementary row operation. Look at the definition here. Definition here is that it's called an elementary matrix if it is obtained by applying exactly one elementary row operation. We are not applying elementary column operation to identity. We are applying only row operation to the identity matrix, right? So this is equal to the first row will remain, the first column will remain the same. So the first column is 1, 0, minus 1. Fine. Minus 5 times the first column plus 2 times plus 1 times the second column. So the first column is multiplied by minus 5. So let me write here. I think I should write here. Minus 5, 0, 5. This is what minus 5 times the first column of A. And then I have to look at 2 minus 1, 1. 2 minus 1 and 1. 2 minus 1 and 1. Yes. Fine. So what I'm going to get is minus 3 minus 1, 6. Is that okay? So just compute it out. Minus 3. I may have done some mistake. So be careful because I do a lot of mistakes. And the third column will remain the same. So third column is 5, 0, 0. So I'll get the same thing. Fine. So I just want you to look at things. Fine. Similarly, if I want to look at A times, the next was E1, 2 here. So A times E1, 2, if I want to look at, then A remains as is. E1, 2 is this. So this will, what it will do is that, look at this part, the second column becomes the first column. So the second column was 2 minus 1 and 1, so it will become the first column. Fine. Then 1, 0, 0 will give me the first column. The first column is 1, 0, minus 1. Please verify it because I do a lot of mistakes as I keep on repeating. Fine. So just verify that this is what happens. So 0 times the first column, 1 times the second column. So 1 times the second column is 2 minus 1 and 1. This is what I had, 2 minus 1 and 1 and so on. Fine. So just try that out. Fine. And as told earlier that elementary matrices are also invertible. I have given you the inverse of them. Fine. If you do not remember it, let's try that out once more to make you understand it. So I would like you to show that, check that EI of C, inverse of this, will be equal to the ith row is being multiplied by C here. So the ith row will be multiplied by the other way around. So it will be EI of 1 over C. And we know that C is not 0. So therefore, I'll have this part. Fine. Similarly, Eij of C, the inverse of this will be equal to Eij of minus C, and Eij inverse will be Eij itself. All right. So just try that out yourself. For example, E1, 2 of minus 5 was supposed to be equal to 1 minus 5, 0, 0, 1, 0, 0, 0, 1. So E1, 2 of 5, if I look at the definition, C becomes minus C, so minus 5 will become 5 here. 1, 5, 0, 0, 1, 0, 0, 0, 1. Multiply these two and verify that you do get I3. Fine. So that's, try that out yourself. The next idea that we have is, as I said, now we are looking at the generalization of row equivalent form. So going slightly, not generalizing, slightly going deeper into row equivalent form. All right. So going further than row equivalent form. And this form is called now, the new form is called as RREF. What we call it as row reduced equivalent form. All right. So it is row equivalent form plus reduced. So there is something extra that we have. So it is row equivalent form itself, but with some extra conditions. All right. Fine. So definition, let me write the definition here. Definition. A matrix A is said to be in RREF or in row reduced equivalent form. If, so not here, I should write here, 1, if A is already in row equivalent form, first thing. So row equivalent form means all the zero rows are at the bottom. There are pivots. The first non-zero entry in each row is a pivot, and every entry below that pivot is zero. I already have that. What I need extra is that pivots should be 1. All right. All the pivots must be 1. All right. 3. All other entry in the pivotal columns are 0. All other entry. All right. Since it is a pivotal column, so there is already a pivot which is 1. All other entry must be 0 as such. All right. So let's look at an example to understand it. Fine. So example. So 0, 1, 2, 4, 0, 0, 2, 4, 0, 0, 1 or 0, 1. All right. So if I look at this is a pivot. These are the pivots. And look at this part. So I get this stair also. So this is in the row equivalent form. Fine. But it is not in RREF, as first part, pivot 2 cannot be a pivot. So all the pivots must be 1. All the pivots must be 1. And 2, all other entries in pivotal column must be 0. All right, fine. So this is not in RREF. Fine. But what we can do is look at the idea here that once I have this, fine, I can always do the following. I can leave the last row as it is. This is still a pivot. I can use this one to make this entry 0. All right. And how do I make this entry 0? By multiplying by, I want to make a 0 here. So 2 can remain for the time being. All right. I can make this 0 by looking at second row should be replaced with, use the third row and replace by -4. So you can see that if I do this operation on the left here, e2 3 of -4, or I should write not like this, I should write, so if this matrix is my B for me, then this times B should be equal to this part. This is what I would like you to see. So e2 3 here is nothing but, it is a 3 by 3 matrix on the left, on the right is 4, but 3 by 3. So second row is being replaced by second row -4 times the third row. Third row there is no change, and there is no change in the first row also. So if you multiply this by B, I would like you to see that the first row will remain as it is. Second row Because of this, it will be this minus 4, so it will become 0. This is what you will get. All right, fine. So you can do some more work on this and then try to see that you can reduce it to 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Fine. This is what you can get. So you can see that you get here I3 coming into play. Fine. And these are the pivots that you have. Fine. So this is in RREF. Fine. You can also take another example. 0, 2, no, sorry, 2 cannot come. So it has to start with 1. 1, 2, 0, 0, 4, 0, 0, 0, 1, 4, 0 here, 2 here, 0 here, 0, 0, 0, 0, 0, 0, 1, and I can have this. So this is again in RREF, because if you look at the pivots, all the pivots are 1. Fine. 0 row is at the bottom. Fine. The pivots are moving to the right. Fine. They are moving to the right. And every other entry in these pivots, these are the 3 pivotal columns, they are 0, every other entry. So I would like you to see that this, if I use this idea 1, 0, 0, 0, this pivotal column, then there is this pivotal column, and 0, 0, 1, 0. If I forget about this part, the last row here, this is nothing but identity. All right. So what we are trying to say is that if I have a pivot, if there are R pivots, I will have IR coming into place. So that's a very important observation. If a matrix is in RREF having R pivots, then I sub R is a submatrix of A. If a matrix A is in RREF and has R pivots and has R pivots, then this happens. All right. So here, if I look at I3 is sitting inside this as such. Fine. So I would like you to understand this. For example, if I look at this matrix again, this is not in RREF. Not in RREF. Why? Because this is not 0, this is not 0, this is should be 1, and so on. So you can keep looking at this. Fine. As a final definition for this class, we have this. This is very, very important definition. Let A and B be 2 M cross N matrices. Then A and B are said to be row equivalent if B can be obtained from A by a multiplication of finite number of elementary matrices on the left. This is very important. On the left, because we are looking at row equivalence. All right. If I want to multiply on the right, then I'll talk of column equivalence. I'm looking at row equivalence. Therefore, I'm looking at multiplying on the left. So what you're saying that I've got B, I should be able to obtain B by multiplying by some matrices E1, E2, some EK times A. All right. So these are your elementary matrices. Well, there are K of them here. I would like you to see that since these are invertible matrices, so you can also get A as just multiply by B is here, multiply by E1 inverse here. This is again an elementary matrix multiplied by E2 inverse, EK inverse. All right. So why are we getting it the other way around? Recall that. So recall that if C and D are two matrices which are invertible, then CD inverse is D inverse C inverse. So they appear in a different sequence. All right. So therefore, I'll get it in a different way as such. Fine. So if A is equivalent to B, B is also equivalent to A is equivalent to itself, things like that. So as a final example, I'll just look at this example to make you understand it. Example. Fine. So let's take some example that I had done earlier. Fine. So I had my augmented matrix with me. So there was this B0. So B0 was 1 1 1 4 2 0 3 5 0 1 1 3. This is what I had. On this I had applied one matrix. So I wrote B1 as 1 0 0 minus 2 1 0 0 0 1 times B0 was whatever I have, it is something. So let me write that 1 1 1 4 0 minus 2 1 minus 3 0 1 1 3. So what we are saying here is that B0 and B1 are row equivalent. Fine. Similarly, we had B2. So I don't remember what exactly I wrote there, but earlier class, but I can also take this as my B2 0 half 1. Fine. So I'm just replacing the third one by something here. Fine. So this times B1, I would like you to see that this is equal to 1 1 1 4 0 minus 2 1 minus 3. Just multiply it out, you'll get the answer 0 0 3 by 2 3 by 2. So as such, if you remember, we had a line here, because it was an augmented matrix that we were looking at. Fine. But here I'm not looking at. So this gives you this. So this implies that this B2, B1 and B0 are row equivalent. Fine. Is that okay? Why they are row equivalent? Basically because if you look at this here, so this is my B0 or B1. So B2 is equal to 1 1 1 4 0 minus 2 1 minus 3 0 0 3 by 2 3 by 2. This is equal to this matrix times B1. So it is 1 0 0 0 1 half 0 0 1 times B1, and B1 is this times this. So it is 1 0 0 minus 2 1 0 0 0 1 times your B0. All right, fine. So this is the one E1 for me, or did I wrote the other way around? No, I wrote the other way around. So this is E2 for you, and this is your E1 for you in the above one. All right, fine. So that's the way to understand, and then you can look at the inverse and things like that. Just try it out. Nothing special. We are just saying that I'm applying elementary operations on the left. So everything, all the elementary matrices will appear on the left. All right. What is important is that if B and A are row equivalent, then I can get finite number of elementary matrices, which will give me the answer. All right, that's important, which they relate. All right. It turns out that those of you who know what is an equivalence relation, then you are saying that this whole collection is row equivalence. All right, they form an equivalence class. Right? That's all in this lecture.